Thanks, computer. Very good. And, okay. All right, so we are going to work on worksheet 6. And yeah, I don't know. I mean, like, ironically, I don't know if it's just me who feels this way, or maybe you do as well. I actually found like question 1 and 2, like, actually I found question 1 to be the hardest question. And then question 3 and 4, to me, are relatively straightforward. Question 1 was hard just because like there was calculations that I had to do. And, you know, I'm a pure mathematician. I don't compute stuff. Maybe you'll find the same way. I think there's value in kind of showing you what to do in 1A and 1B. So why don't we start with 1A? And then we'll kind of do 1B together if you want, or I'll show you kind of how to set it up and we can talk about it. But the way that you handle them is actually really quite different. So we'll start with 1A, and I'll give you a little bit of time to work on it. So this is the statement, you know, that you've got this isomorphism from Z20 to Z20. And isomorphism. And phi of 5 equals 5. What are the possibilities? For phi x. Okay, so I'm not gonna lie, I hated these questions when I was an undergrad. But now it's my turn to pass that hatred on to you. So let's take a couple of minutes here and see if we can't grind this out. I'll give you about 5 minutes, but again, don't hesitate to ask questions. Like if within a minute or two you don't have anything, say something, because there's a hint that I can give that'll really open it up. But there's a nice little, I don't want to call it a trick, but hopefully you see it. Otherwise, it's going to make your life a little bit harder. Okay, so let's spend 5 minutes and let's see if we can get this. Anyone managed to figure out what phi should be? Let me just check my answers very, very quickly here. I got, if you got any examples, did anyone, like there's obviously one, right? There's like the identity map, right? The identity map will certainly send phi of 5 to 5. Did anyone get any others? Or alternatively, how many did you get? There it is, 1, 2, 3, 4. Okay. So X maps to, like, I assume that's maps to, right? So X maps to negative X. Does that work? So note that if we took, for example, phi of X equals negative X, then we would have phi of 5 equals negative 5, and that's equal to 15, and that's different than 5, right? So our function wouldn't be well defined in that case, right? So X mapping to negative X actually doesn't end up working. It doesn't give us an answer, yeah. Right, do you see why that one doesn't work? Like why that one's broken? All right, because negative 5 is equal to 15 in Z20, yeah. Okay, so what do we need? So I actually got 5 answers. Did anyone else get 5 answers? No? Okay, so here's kind of the critical thing. And this works really because we're in a cyclic abelian group, right? Now, this doesn't work for most groups, but it does work here. There's something very, very special. So basically I claim, and I think this is discussed in the book at some point. So I claim that phi is entirely determined by where it sends 1 to. by phi of 1. Okay, so what I mean by this is for every single possible, and this is actually not just isomorphism, this is every homomorphism from like Z20 into another cyclic abelian group, where if you give me a unique homomorphism, it has a different value of phi 1, and for every valid number phi 1, you'll get a different homomorphism, okay? So every homomorphism is uniquely represented by some number phi 1. And to see this, note that if we take phi of some number n, well, again, this is actually an integer, right? Or it's an equivalence class of integers, but that's fine. So n is the same thing as adding 1 to itself n times. Right? We know that. That's not crazy. That's literally the definition of n. And then because this is a group homomorphism, we can split this up like this. And that gives us n times phi of 1, right? So whatever the function is some number is phi of 1 times the number that you plugged in. Okay, so in some sense, maybe let me write it like this. Phi x is kx for some k. Right? Which is really, really nice. This tells us that no matter what, and again, it doesn't even have to be an isomorphism here. This is a homomorphism. No matter what homomorphism I give you from Zn to Zm is uniquely defined by what it does to phi 1. Every single one of them looks like one of these linear maps, k times x. And the value of k is whatever 1 maps to. Okay, does that make sense? Does everyone see that if you just know what phi of 1 does, then you've got everything, and you know what the homomorphism does to everything because of this nice little property here, right? It's kind of like, again, when you think about linear maps, if you know what it does to a basis, right? If you think about linear algebra, if you know what a linear transformation does to a basis, you know what it does to everything because you can write it in terms of that basis. There's a sense here in which 1 is the basis element for Zn because every other element can be written in terms of 1. Right? It can be written as by adding 1 to itself a whole bunch of times. And then the group homomorphism splits over that. Okay. So what this means is that whatever we know that phi of 5 is equal to 5, right? So since phi of, or let's say 5, let me start with 5. So I'm going to say since 5 is equal to phi of 5, and we just showed that's equal to 5 times phi of 1, right? So what we want to know is for what values is this statement true in Z20? So what values of phi of 1 satisfy 5 is congruent to 5 times phi of 1 mod 20. Now, when I said that this is the hard question, it's because I actually don't know how to solve this equation without just brute forcing it, right? Basically, what we're asking is, we want the solutions to this. Okay, now let's just go through. First of all, 1 is definitely an answer, right? So x equals 1 is clearly a solution. Can anyone think of another one? Is that the only one? Can anyone just think of another solution? 5, yeah, absolutely, right? 5 times 5 is 25, right? We reduce that mod 20, we get 5. What are the other ones? Is there another one? 913, sure, yeah. So 45 and 65 also both work. Is there more? And you can see, like, I don't know if you guys have some sort of special trick in doing this. When I do this, I just literally go through all the numbers. You can immediately throw out all the even numbers, right? The even numbers won't work because they won't give you a remainder of 5. So you just have to check the odd numbers. There is another one, 17, exactly. Right? 17 times 5 is 85. Mod 20 is equal to 5. So these are the answers here. Okay, everyone agrees? And none of the others work. So the answer is phi x is either, so the only possible options, nine x, 13x, and 17x. Okay. And okay, so without kind of like doing the whole other question, so this wasn't too bad because 5 is a really nice number and 20 is a nice number, right? So we were kind of able to do this by hand. And I'm going to show you in a second how I would actually do this. I wouldn't kind of like compute them all in hand. Let's do B. I'm not going to give you time to do B, but let's just think about how we would do it. So B is the exact same thing, only we now have Z50 to Z50, right? Just to make it so that now there's like 49 numbers that we need to check. And we know that phi of 11 is equal to 13, right? So there's first of all, there's a couple of things that we can immediately tell here. We can do immediately the same thing, right? So we know that 13 is phi times 11, or phi of 11, which is 11 times phi of 1. That's still true, right? That's always going to be true for homomorphisms between cyclic abelian groups. Thus, we need to solve 13 is equal to 11x mod 50. That's way worse, right? Like this one, we're probably not going to do this one just by going through all the numbers from 0 to 49 and seeing which ones work. But this one I do know how to solve. And how would we do this one? And why, and then I guess the bigger question is, why didn't this work in part A? Anyone know? Or actually, maybe let me write this as a different way. Let me write this as 11x equals 13. It's the exact same equation, right? There's just a reason that I want to do it this way. Nobody sees it? Okay, let me excuse me, let me kind of give you how this would work. 11 and 50 are coprime. Okay, and since they're coprime, that means 11 is actually invertible, right? It has a multiplicative inverse. Has a multiplicative inverse. So we could solve this to get x is equal to 11 inverse times 13 mod 50. Now, finding 11 inverse, though, isn't much easier unless you can eyeball it. So out of curiosity, does anyone see what the multiplicative inverse of 11 mod 50 is? Because if you think about it, you can actually find it. Anyone know? It is actually possible to guess and check this one. No on A. Okay. The multiplicative inverse is 41. And you might say, like, okay, clearly there's no way anyone was going to figure that out, right? What's 41 times 11? It's 451, right? So this does actually work. So I just double checked it. I plugged it into a calculator. This actually works, right? 11 times 41 equals 451, which is congruent to 1 mod 50. Okay, how did I actually get that, though? Because there's no way I know what 11 times 41 is. I didn't just eyeball that. What I did know, though, is that 11 times -9 is -99, right? or maybe let me write this in a different way. So 50 times 2 plus 11 times -9 is equal to 1. So if I reduce that mod 50, tells me that 11 times -9 is congruent to 1 mod 50. And -9 is not a number between 0 and 49, but that's fine. We know how to convert -9 into a number, where I'm just going to add 50 to everything, and that's going to give me 41. Okay, so that's how I would find that. And so what we're going to end up getting is that x is equal to 41 times 13 mod 50, and 41 times 13 is 533. So this is congruent to 33 mod 50, like so. Okay, and you should all, okay, so the reality is too, you might be like wondering, okay, you just pulled a whole bunch of like number theoretic nonsense on me. Like, how would I have ever come up with this, especially if I didn't have a calculator? You'll notice that this is Bezout's lemma, right? The fact that that 50 and 11 are co-prime, their GCD is equal to 1, means that I can find an integer solution to 50m plus 11n is equal to 1. And does anyone remember what the algorithm you use in order to find the solutions to Bezout's lemma is? Remember what that's called? I think some people learned it in 102 and some people didn't. I think it might actually depend on like who your professor was. But for this, you use the Euclidean algorithm. Did you all learn that? I don't actually know if they teach it in 102 anymore. They teach you the Euclidean algorithm? Yeah? Okay, so you can use a Euclidean algorithm to compute the GCD of two numbers, and then you can reverse the Euclidean algorithm to actually find the solution to Bezout's theorem. And if you find the solution to Bezout's theorem, this is why this is why 11 has an inverse mod 50, is because if I take Bezout's lemma and reduce it mod 50, I'm going to get 11 times the number is equal to 1, right? And that's precisely what it means to be invertible. Now, the problem with part A, doing this in part A, is that clearly 5 is not co-prime to 20, right? So I can't multiply both sides by the inverse of 5 because 5 doesn't have an inverse. So that's sort of the problem. So the reality is that in part A, you kind of have to eyeball it. Now, what I would say is in practice, like I said, I don't know how to solve that. Maybe there is a number theoretic technique to do that, and I don't know about it. But what I'm going to do is say the following. What you should do in this case is use a computer, right? So I'm going to use and you can do this using any programming language. I would do it using Python because I think that's the one language I can guarantee you all probably know, because I think that's what they teach you in first year. And then the real sweet thing about this is that if you're comfortable with Python, this is a one-liner, right? So let's say we wanted to do problem A, right? So namely, we're trying to solve 5x is congruent to 5 mod 20. So we can use, what is this called? I think it's called set comprehension. X for x in range 20 if, what do I want here? If 5 times x mod 20 equals 5, and there are the 5 numbers, right? Does everyone see that? All right, so I basically use a computer to do it. If you want, you could write a for loop and an if loop, but or an if thing. But basically, Python has set comprehension, which makes this really, really nice. Same thing if we want to do it for Z50, we're just going to change this to 50 here, and we should get 33, right? Oops, no, oh, something, sorry. I don't want 5s here. We're doing 11x mod 50 is 13, right? So we get 33. So, I mean, I definitely think you should, in these sorts of situations, use a calculator rather than computing them by hand. I think we could get x congruent to 1 mod 4. What do you mean by that? Like where You want to reduce it somewhere, like somehow you manage to, and which part are you talking about, A or B? Okay, sure. Possibly. I assume you're trying to use the remainder theorem or something like this to do that. Because like you can't, no, you can't. Oh, you're right. It does actually work out to be congruent to 1 mod 4. You're right. It does work out that way. I'll have to think about that. That might be, that doesn't seem like it should work in general. It does work out in this question, but let me think about it. Let me see if I can prove that. Let me see if I can prove that number theoretically. That is a really good observation, though, Hongwei, that it is x is congruent to 1 mod 4. That is a really good point. And you're right. It definitely does work because every multiple of 4, as you do 5 times 4, you get a 20, right? So you just kind of are like going around the circle, right? I think that's kind of what you picked up on, right? So every multiple of 4 just goes back around the circle one more time. But again, either way, I would kind of use a calculator for that. Even if you're doing the second part B, I would use a calculator just to make your life a little bit easier. Okay, so that's that. And hopefully that made sense. And again, there's some, kind of like a little trick there in the sense that we, I use this fact that a homomorphism from between cyclic abelian groups is entirely determined by what it does on a generator, right? Okay. So let me reshare my screen here. What do you guys want to do next? Is there a question that you want to see? Like if you look at the problems, is there one, because I'm probably not going to get to them all. Is there one that you prefer? Because I claim that like, you all might not feel this way. I claim that problem 3 and problem 4 are for the most part relatively straightforward proofs. Problem 4 is maybe a little bit harder than problem 3, but problem 3 is just do the definition, right? So is there one that anyone wants us to work on? Also, 2b doesn't seem to be related to 2a, so I don't know if there's a thing there. All right, I'm going to skip 2 because nobody seems to be interested in it. Maybe we'll go straight to 4. Okay, let's do question 4 next. So I'll give you a little bit of time to try and work on this. Okay, so let's do question 4a first. So suppose, and I gave you this as an exercise last time. So in theory, this should be really, really easy because you all did my exercises that I told you to do, right? So suppose that phi mapping G to G prime is an isomorphism. We actually don't need isomorphism for this. I mentioned last time we only need injective. Show that the order of G is equal to the order of phi of G for all G in G. And I'm going to say, nope. Phi only has to be injective. Okay, so we don't actually need it to be an isomorphism. We don't need surjectivity. That doesn't make a difference. We only need injectivity. So I'll give you 5 minutes to try this, and then we'll take it up. And remember, you already have one, right? We know that the order of phi of G divides the order of G. So if you can get the other direction, then you're done, right? So maybe let me write that as a hint. Maybe note number 2. We know that the order of phi of G divides the order of G. So show the other direction. Like that. All right, so 5 minutes and let's see where you get. Okay, so I'm going to start again. Before I actually start, though, I want to confirm, Hongwei, absolutely, you're right. 1 is congruent to 1 mod 4, or x is congruent to 1 mod 4. And I should have seen this, but you are 100% correct. So thank you for pointing it out. If we want to solve this, this is equivalent to saying, can we solve this? 5x minus 5 equals 20n for some n. And that's the same thing as saying x minus 1 equals 4n for some n. That's not how we spell some n. And that's the same thing as saying x is congruent to 1 mod 4. So absolutely you're right. And that, of course, makes this much, much easier. Yeah, so good call. Okay, now for this one, we have, what is that thing on the bottom of my screen? Okay, whatever. So like I said, we already know that the order of phi g divides the order of g. So now we need to show the other direction. And this really suggests to us, again, that we're probably going to try and show that g to the order of phi g is equal to the identity, because that will give us this division relationship. So what I'm going to do is say, well, no, we know that this is true. So if I take phi g and raise it to the order of phi g, that's the identity, right? And then I know as well that I can take that phi g inside because this is a group homomorphism, right? So because this is a group homomorphism, let me draw my brackets really, really big here. I can put that inside like so. And if we look at this equation, what does this say? Phi of this thing is equal to the identity. Well, that means that g to the power of the order of phi g is in the kernel of phi. G to the order of phi of g is in the kernel of phi. But if phi is bijective, or in particular, the only thing we actually need here is injectivity, that's equivalent to the kernel being trivial. So, but since phi is injective, it's trivial. So that tells us that g to the phi g must be the identity. Right? And that's exactly what we wanted, because this implies that the order of g must divide phi g. Right? So both divisions, so we now have the order of g divides the order of phi g, and the order of phi g divides the order of g, so they must be equal. Like so. Okay, any questions? No? Okay, let's do then 4b, which is nice and fun. So again, we have, and this time we do need that it's an isomorphism, okay? So we want to show that the centers are preserved. And again, that's in some sense obvious, or at least not obvious, but expected. Because if two groups are isomorphic, they are the same group, so they should have the same centers, right? Okay, so I'm going to give you 5 minutes, see if you can prove this. Like I said, this one you absolutely do need that it is an isomorphism. You are going to use both injection and surjection to prove this. Okay, so yeah, that's been about 5 minutes. This proof is a little bit on the longer side. I kind of want to get a start on it a little bit earlier, just because, as always, this is a double subset inclusion, right? I'm trying to show that two sets are equal. I want to do a double subset inclusion. Now, it's possible that one inclusion is automatic. I don't really remember, but either way, I'm just going to prove them both. So, solution, let's show this inclusion to begin with, right? So let's show that the image of the center is contained in the center of the other group. All right, so what are we going to do? We're going to pick an element in the image of the center, right? So I'm going to use K to denote those elements. So let's let K be some element in phi z of g. And let's write that as phi g for some G in the center of G, right? Because that's what it means to be in the image. Okay, now I want to show that K is in the center of G prime. So I want to show that it commutes with every element of G prime. So I'm going to let K hat be just an arbitrary element of G prime. We want to show that K prime is K prime K, right? i.e. that K commutes with every single element of G prime. Okay, but since phi is surjective, so here you see I'm using the bijectivity properties. Since phi is surjective, there exists some G hat in G such that K hat is phi of G hat. And moreover, since G, like little g, not G hat, little g is in the center, it commutes with G hat, right? And since G hat G equals G hat, then we're going to get phi of G hat G. That's going to be K hat K because it's a homomorphism. This is going to be equal to phi of G hat, since G and G hat commute with each other. And that's going to be K hat. And that's exactly what we wanted, right? K and K hat commute. So thus, K is in the center of G prime. And that gives us that phi Z of G is contained in Z G prime. Okay, so that's one inclusion. Now we have to do the other inclusion. The other inclusion is actually going to use injective. I think it's actually, if I recall correctly, it uses injectivity and surjectivity. So let's show that the center of G prime is contained within the image. So fix some K in the center of G prime. And we want to show that it is in the image of G prime. Well, since phi is surjective, there's something that maps to it. And there is actually a unique element which maps to it. That's what the exclamation mark means, that there's a unique thing. So there's a unique element in G such that phi of G is equal to K. Thus, to show that K is in the image of the center of G, it suffices to show that little g is in the center of G. So it suffices to show that G is in the center of G, since then we're done. So I need to show that G commutes with every element of G. So let's pick another element. So let's let G hat be some element of G. And let's let K hat be its image. Since K is in the center of G, it commutes with everything. So we know that, what do I want to say? So phi G hat is going to be K hat. K is in the center, so it commutes. So that's going to give me phi hat G. So if we ignore everything in the middle, we get this. And I want to show that the things inside the phi are equal. Why do I get that for free? Why do I immediately know that? Since what? Okay, yeah, phi inverse exists, so we certainly could use that. I agree, and that absolutely would do it. I think that there's like a faster way that we could get there, but you're absolutely correct. That would definitely work. So we could apply phi inverse to both sides, and then we would get that these two things are equal. Alternatively or equivalently, phi is injective. But that's a perfectly valid thing. Saying the phi inverse exists, so we can apply that. I like this a little bit more because to me this feels a little bit more elegant. This is precisely the condition of injectivity, right? If phi of one thing equals phi of another thing, then the arguments of the function have to be equal, right? So because phi is injective, g hat is g hat g. And so this tells us that g is in the center of g. Which in turn tells us that k is in phi zg. So zg prime is a subset phi zg. And we're done because we did both inclusions. Okay. All right. So that finishes up our lecture. Man, that was pretty close. I went a little bit over time, I think. I'll hang around if anyone has any questions, but otherwise, I think that's going to take care of it. Make sure you can do exercise 3. They're relatively straightforward, but they're really good exercises. Okay, so problem 3 is really good. 2A is pretty straightforward. 2B is kind of nasty in that you just have to compute some stuff. But really make sure you can do 3 and 2A. Okay, those are not too hard to do and really cement your understanding of groups and homomorphisms and isomorphisms and kernels and images and these sorts of things. Okay, everyone? So like I said, I'm going to hang out. Otherwise, have a good weekend, and I will see you on Monday.